All right, well, welcome back. So in the previous lesson, we started to have a look at the sequences and series chapter. So last time we started to have a look at what defines a sequence, what are the various forms of a sequence. We also had a look at what can we do to find a general term formula for the given sequence. We also had a look at limits involving sequences as well, as this will actually be an important part of this chapter, uh, basically having to look at limits of a sequence. We also have to look at sequences, limit properties for sequences, and basically if they converge or diverge, that's what we also had to look at before. Uh, some other examples involving uh, convergence or divergence of sequences. And basically, we also had to look at some increasing or decreasing and bounded sequences as well. And that was basically it. And we also had to look at some examples, but I think last time I assigned these ones as um, exercises. So these are the answers to B, D, F, and this one I still had to do, but those three are the ones I assigned, so those are the answers if you want to have a look at them. So anyways, let's get started with this section here. So this time we're going to be talking about the series of real numbers. So we should be a little bit familiar from grade 11 that we had to look at sums of arithmetic series, geometric series, sums. So for example, let's take the value of pi here. So we know that pi as a decimal expansion is going to be given by 3.1415926 and so on. So that was from last time, or the values of pi. However, we could also write pi as a series. Why? Because here we could write this as pi, which is equal to 3 divided by 1, or 10 to the power of 0, let's put it, plus 1 divided by 10 to the power of 1, plus 4 10 to the power of 2, 1 divided by 10 to the power of 3, and so on. So we could also express pi as a series as well. So in general, if we try to add the terms of an infinite sequence given by this, then we get an expression of the form a1 plus a2 plus a3 plus so on plus an and so on as well. Or we could also express this as a series using the sigma notation we had a look at back in the first chapter. So we could express this infinite series as the sum from n is equal to 1 to infinity of ai or an, which has the exact same representation as the one above. So this is called an infinite series or just series for short. And we're already familiar with some examples. For example, from section 1.7, we had a look at a finite number of terms in a sequence given by this series. So we know that this is actually equal to n times n plus 1 divided by 2. However, let us take the limit as n approaches infinity. So that means what we want to do here is take the limit. So we have the limit as n approaches infinity of the series. So n here from I is equal to 1 of I. So basically, as n is approaching infinity, we're sending this n to infinity here. So because that this series here is equal to this expression over here, we could just substitute that in so that we get the limit as n approaches infinity of n times n plus 1 divided by 2. Now here we could automatically see that as we send n to infinity, that this value would also be approaching infinity as well. So that's something useful about series. We could also try to take the limit of its nth term and see what happens as n approaches infinity. So it's possible to determine whether the series converges or diverges, for example, like the one that we have here. So the series, the sum of all natural numbers from 1 to n, is actually going to diverge. So the next session or next section, we'll have a look at some techniques that we would like to use in order to determine whether the series converges or diverges. However, let's have a look at another example. Let's have a look at the series of 1 divided by 2 to the power n, which is given by this expression over here. So what value does this converge to, and why? Well, let's have a look. If we keep on adding more terms, so we're starting with 1/2, adding a quarter makes it 0.75, adding an eighth makes it 1.875, 1/16 will make it about closer to 0.9 something. And if we keep on adding more terms, we see that the values would actually get closer and closer to 1. So the question here is, so does the series converge to 1? So that's one of the questions we'll have a look at later on. But one of the key things here is that since the value is getting closer to 1 as we add more terms. So that's the thing we want to keep in mind here. All right. So we use a similar idea to determine whether or not a general series has a sum. So we actually considered the sequences of partial sums. So for example, we call it S1 to be just the first term, S2 to be the first term plus the second term. The third term, S3, to be the first term plus the second term plus the third term. Or, in general, we could have that Sn to be A1 plus A2 plus A3 plus so on, plus An. This is equal to the sum from I is equal to 1 to n of Ai. So this is called this sequence of partial sums, or we say that if the sequence of partial sums converges, then the series itself would also converge as well, which we could actually define using the following definition. So let the sum of a from n is equal to 1 to n, or 1 to infinity of an to be a series, and we let Sn be the nth partial sum given by this expression over here. Then we say that if the sequence of partial sums converges, so that means the limit as n approaches infinity of the nth partial sum approaches to some number s where s is a real number, then we say that this series, this infinite series, is also convergent, and that this series will equal to this limit and equal to this limit here as well. However, if the sequence of partial sums diverges, meaning that it does not converge to a real number, for example, it converges to infinity, then we say that the series diverges. So let's have a look at an example. So let's determine whether this series converges if the nth partial sum is given by this expression. So using definition 7.2.1, if we assume that this converges, we have to find out what this limit is. So what we have to do is just take the limit as n approaches infinity of Sn. So that means we take the limit as n approaches infinity of 2n divided by 3n plus 5. And this is equal to the limit as n approaches infinity of 2 divided by 3 plus 5 divided by n, because we're it's almost like finding the horizontal asymptote here. And as n approaches infinity, this is going to go to 0. So what we're just going to be left with is just 2 over 3. So because s 2 over 3 is a real number, the series converges, and the value is 2/3. So that's by using definition 7.2.1. Good. So now let's consider an important series called the geometric series. So we're given this series here, where a is not equal to 0. So let's determine the values of r such that the geometric series converges and diverges. All right, so one thing we should first have a look at is when r is equal to 1. So case 1 is when r is equal to 1. Oops. When r is equal to 1. So when r is equal to 1, then we have the partial sum given by the nth partial sum. So then the nth partial sum is given by so we have a plus a. So because r here is going to be replaced with 1, and also that the r squared is going to be 1, r cubed going to be 1, and so on, they're all going to be 1. So that means we're just going to be left with a plus a plus a plus so on until we reach the 8th term. So that is just going to be the sum from I is equal to 1 to n of just the value of a. Now, because a is non-zero, this is just going to equal to NA, which is the nth partial sum, right? So let us take the limit as n approaches infinity. So because we want to determine when it converges or diverges, we have to take the limit as n approaches infinity of the nth partial sum. So that means the limit here as n approaches infinity of Sn of the limit as n approaches infinity of n times a. Now here, as we send n to infinity, this is actually just going to go to infinity as well. So that means the limit here is infinity. So therefore, the series diverges when r is equal to 1. Okay, so now let's consider another case. So let us say when r is not equal to 1 then. So case 2 is when r does not equal to 1. So let's say the nth partial sum then is given by so we have a plus AR plus AR squared plus so on until we reach the AR n minus 1. Because of this one here, we adjusted the index so that's n minus 1, not n, just n here. Okay? So let's call that equation 1. So we'll call this n as n, and we'll call that equation 1. Equation 2, let us say we multiply both sides by r. So we have r as n, and I'm going to align the terms. So if we multiply the first equation by r, what we get is going to be AR plus AR squared plus so on, ARn minus 1, and plus AR to the n. So that's going to be our second equation. So let us subtract the two equations. So subtract 1 and 2. So we're subtracting 1 and 2, so that we could attain that Sn minus Rsn. On the right-hand side, when we take the difference, these middle terms here all cancel out, and what we're just going to be left with is just this A and minus A r to the n. So we have A minus A r to the n. Good. So now we could actually common factor out some terms here. So on the left-hand side, we could common factor out the Sn so that we have Sn times 1 minus r. On the right-hand side, we could common factor out the A so that we have 1 minus r to the n. Now, dividing both sides, we're solving for our Sn here. Sn here is just going to equal to A times 1 minus r to the n divided by 1 minus r. So A here is usually called the first term of the series. So A is called the first term, and R is called the common ratio. Ratio of the term. Okay, so now let us consider two subcases here for R here, because we have to make sure that the values of R make sense. Now, obviously, when we substitute R is equal to 1, we get something that is not good. So let's consider R to be greater than 1. So this is subcase A. So this is subcase 2.1. When we consider R to be greater than 1, what we get is that, well, by taking the limit as n approaches infinity of Sn to be the limit as n approaches infinity of A times 1 minus r to the n, 1 minus r. Now, obviously, the only term that is actually going to be affected is this one. Now, this term over here looks like an exponential function here. For example, over here, if we draw the graph of this, r to the n, because r is greater than 1, it will look something like this as we shoot it to infinity. So that r is greater than 1. So as we see, if we set n to approach infinity, so these points here are just the discrete values 1, 2, 3, 4, so on, we see that the value will actually just go to infinity. So that means this term also goes to infinity as well. So because this term goes to infinity, that means the entire series is also going to go to infinity. So that means the series diverges when r is equal to 1, or r is greater than 1. Okay, let's consider when r is less than -1 here. So if we consider r less than -1, same thing. So here when r is less than -1, so I'm choosing -1 here this time. You'll see why in a little bit. By taking the limit as n approaches infinity of Sn, so we have the limit as n approaches infinity. Now I could also write this as -r to be greater than 1, right? So that means I could write this as A times 1 minus -1 to the n, r to the n, divided by 1 divided by r. Now, because of this, n to infinity, this part here, we don't know whether it diverge. We know that this part here is just going to diverge, And we also know that from the r is equal to 1 case, that r is greater than 1 case, that this is also going to diverge here. So both of these combined will just diverge overall. So that means the series here also diverges. Or we say that it does not exist here. So the series diverges when r is less than -1. So I'll copy the same page down here. We have two more subcases to look at. So now we're having a look at when r is smaller. So let's say that when r is between 0 and 1. Now, can r equal to 0? Yes, that is possible. Because if we substitute r is equal to 0 here, 0 to the power n is just going to be 0. So we just have this part here, and that would also still converge. Okay, so that means we could also include r 0 as well. So 0 less than r less than 1. Now, because of this, we now have that when we take the limit of Sn, the limit as n approaches infinity, a times 1 minus r to the n divided by 1 minus r. This value, because r is small, we're going to have an exponential function that looks like this now. So because it's decreasing, r is small, it's actually going to approach to 0. So that is when r is between 0 and 1. So that means this value, r to the power n, is going to go to 0. And because of that, we're just going to get a divided by 1 minus r. So it does converge when r is between 0 and 1. And one more case that we had to look at. So subcase 2.4. When r is between -1 less than r less than or equal to 0. Now, because of this, so when we take the limit as n approaches infinity, as n, the limit as n approaches infinity of a times 1 minus r to the n, 1 minus r, because r is also small here, we could also say that it actually converges as well. So actually, I could also write this as 0 less than or equal to absolute value of r less than 1. So I could also write it like this. And because of that, we know that from the previous subcase, it's r to the power of n is going to go to 0. So this value goes to 0. And what we're left with is just a divided by 1 minus r. So we have found all the cases when the geometric series converges and diverges. So in general, the geometric series converges when r, let's put an absolute value of r, is less than 1. So meaning that it's between -1 and 1, non-inclusive. So it looks like this. So that's the region where it's going to converge. Other than that, it's going to diverge. And the sum is given by this. So we have the infinite sum of a, r, n minus 1. This is going to equal to a divided by 1 minus r. And diverges otherwise. Okay, so that's good. So let's have a look at the next part. So we now define what the geometric series is. So the geometric series, given by this, we say that is convergent if r is less than 1, the absolute value of r is less than 1, and is equal to this. And otherwise, if r is greater or equal to 1, then it diverges. So let us try to determine whether the geometric series given by this is going to converge or diverge. And if it converges, let us find the value. So first thing, let us observe that here, that the first number is going to be 5 here. So here we know that a is equal to 5. Another thing that we could also observe is that every time we go from the first to the second to the third to the fourth, we're always going to be multiplying by 2/3. So see, if I take this multiplied by 2/3, I get this value over here. Multiply here again, I get 2/3, or multiply by 2/3, I also get this value. Multiply 2/3 to get this value here. So that means the common ratio here is going to be 2/3. And we also had the negative outside, so that's also important. This negative sign, because it's going to go from negative to positive to negative. Because of that, we also had to add a negative sign to the common ratio. So that means the common ratio is negative 2/3. Now, since the absolute value of r, which is equal to the absolute value of negative 2/3, which is 2/3, is less than 1, the series, geometric series, converges. All right, so when we have that, a is equal to 5, r is equal to negative 2/3, so that means the infinite sum of 5 times negative 2/3 to the power n minus 1, this is going to equal to the first term, which is 5, divided by 1 minus negative 2/3. And so once we add the terms up, so that's going to be 5/3, and this value is just going to equal to 3. So that's the value of the geometric series. Let's have a look at another example. So let's determine whether the series of 2 to the power 2n multiplied by 3 to the power 1 minus n converges or diverges. Now, first thing is that we should note that the sum, we could rewrite this a little. So 2 to the power 2n, 3 to the power 1 minus n. I could write this as the infinite sum of 4 to the power n for the first one. And I could also write the second part as 3 to the power negative 1 or n minus 1. Because I have the negative exponent, I could move it to the denominator. So I have this 3n minus 1. And because of the first term, we want it to be n minus 1 for it to be the correct geometric series. I could write the numerator as this. 4 times 4n minus 1, 3 to the power n minus 1. Good. So now I could actually just bring the 4 outside, and this would actually just be a term by itself. So using exponent rules, we have 4/4 n minus 1. So that is the geometric series. However, note here, 4/3 is larger than 1. So since the absolute value of r is greater or equal to 1, the geometric series diverges. Okay, so that's good. So that's the case when the geometric series will diverge. Okay, so let us find the sum of the series given by the sum of from n is equal to 0 to infinity, x to the n, where x is less than 1. So because x is less than 1, it converges. Okay, so let's write down the series first. So this is called, so we have that xn. We could also write this as the infinite sum, n is equal to 1, x to the power n minus 1. And once we write this down, what we get is 1 plus x squared plus so on, xn, also so on, or xn minus 1. Because this is a geometric series, we have that a is equal to 1, and we also have that r is equal to x, where x is less than 1. So by using the geometric series formula, this is equal to just the 1 divided by 1 minus x. So therefore, we have that this sum of x to the n equal to 1 divided by 1 minus x. And that is something called the power series or the Maclaurin series that we will actually have a look at later on in the chapter. Okay, so now let's have a look at a different type of series, not the geometric series, but something that you might see in common. So we want to show that the series here is actually convergent, and we also want to determine the value of it. So first of all, let us rewrite this term over here as two terms. So we're going to use partial fraction decomposition here. So by partial fraction decomposition, we have that, well, 1 divided by n times n plus 1. This, I could also write this as a divided by n plus b n plus 1. So that means I could add this as a n plus 1 bn, whole thing divided by n times n plus 1. That's also equal to a plus b n plus a. And the whole thing is divided by n plus 1. So obviously, when a is equal to 1, so a is equal to 1, and a plus b is equal to 0, so that means b has to be negative 1. So that means I could write this term as 1 divided by n minus 1 divided by n plus 1. Okay, so let's write this inside the series. Okay, so we have 1 divided by n minus 1 divided by n plus 1. So that's what we have. But now let us consider the nth partial sum. And see what we get. So writing this out, we have from I is equal to 1 to n of 1 divided by I minus 1 divided by I plus 1. If we expand the terms a little, so we could make some observation. So one thing is that, well, the first value is going to be 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. And if we keep on adding the term so that until we have 1 divided by n minus 1 plus 1 divided by n, 1 divided by n minus 1 divided by n plus 1. So what we have here now is that all the terms in between, so we have this canceling, we also have the 1/3 canceling, we have the 1/4 and 1/4 that is in between, and the stuff in between cancels except for the last term. So we only have this 1, and we also have this 1 divided by n minus 1, including the negative sign. So that means the sum here of 1 divided by I times I plus 1 is equal to 1 minus 1 divided by n plus 1. Now, let us take the limit on both sides. So this is the nth partial sum, right? So by taking the limit as n approaches infinity of Sn, so that means we're taking the limit of this sum. So that means if we take the limit as n approaches infinity of 1 minus 1 divided by n plus 1, you see that as n approaches infinity, this number is going to go to 0. And what we're just going to be left with is just going to equal to 1, right? So therefore, the series converges to 1. Now, this is a popular series known as the telescopic series. And basically, you have the first term and you have the last term, and that will actually become your sum. But in the end, it will actually just converge to 1. So it's called the telescopic series that we just investigated here. Okay, so let us have a look at the next part. Now we want to show that this series diverges. Now, obviously, if we have a look at it by itself, we don't exactly see any patterns. However, let us consider the nth partial sum, or actually, instead of the nth partial sum, let's have a look at the 2 to the nth partial sum. So let's say we let s of 2 to the power n be the 2 to the nth partial sum. Why we consider this? Well, let's have a look at each of them. S to the power 1, or s of 2 to the power 1, is going to be the second term, just the first and the second term, meaning that we'll just have 1 plus 1/2. Nothing just yet. Okay. Okay. For the second one, s 2 to the power 2, so that's going to be 4. We're going to get 1 plus 1/2 plus 1/3 plus 1/4. However, note that these two terms here, that is greater than 1 plus 1/2 and then plus 1/2 plus another 1/2. Okay, so that's 1, 2, and 3. Actually, no, it should be 1/4. Each of them are greater than 1/4. Or in general, that is equal to 1 plus 2 over 2, right? Nothing here just yet, but let's have a look at the third one. So that means we have a look at s2 to the power 3. That means we'll have the terms 1 plus 1/2, 1/3, 1/4, 1/5, 1/6, 1/7 plus 1/8. The first part over here, it's also going to be similar as to this part here. And we're also going to have a look at the next 4. Because this is all greater than 1, 1/2, 1/4. I'll use a different color. So this is greater than 1/4 plus 1/4, and then plus the 1/5, or plus, that's going to be 1 divided by 8 now. 1/8 plus 1/8 plus 1/8 plus 1/8. Because clearly, each of the terms here, 1/5 is larger than 1/8, 1/6 is larger than an eighth, 1/7 is larger than an eighth, and this one doesn't really matter. But the point here, this is going to be equal to 1 plus 3 divided by 2. So we should start to see a pattern here. This 1 here corresponds to this 1. This 2 corresponds to this 2. And this 3 corresponds to this 3. So we can make some kind of relationship. We could also see that s to the 2 to the power 4. This is also larger than 1 plus 4 over 2. And we could also see that s to 5 is also larger than 1 plus 5 over 2. So in general, we could also say that, well, s2 to the power n, this is always going to be larger than 1 plus n over 2. Now I'm going to use a comparison test here. If I show that this diverges, the series here is also going to diverge. So let us take the limit as n approaches infinity on both sides. Well, on the right-hand side first, because here, this is going to go to infinity. So we know that this diverges. So we're going to use a comparison test here. So since 1 plus n over 2 diverges, that means s divided by 2 to the power n also diverges. And so that means the harmonic series up here actually diverges as well. So therefore, the sum diverges. Very good. All right. So now let's have a look at one theorem that is an important theorem whenever we want to test whether a series converges or diverges. So it says here, if the series is convergent, then that means the limit of the sequence has to equal to 0. Now let's prove this. So it's a pretty easy proof. So let's say that since this series is convergent, so since this series is convergent, then what does that mean? That means the sequence of partial sums also is also convergent. Partial sums is also convergent. Good. Now, because I could write this as the limit as n approaches infinity of Sn is equal to S. Also, I could also write an as Sn minus Sn minus 1. That will actually give me the value of an, the nth term, right? And so now, the limit as n approaches infinity of an, this is equal to the limit as n approaches infinity of Sn minus Sn minus 1. Each of these are going to equal to S. So because of this here, because it's convergent, so that means we just have S minus S. This is equal to 0. So that means we have shown that this is equal to 0. So therefore, the limit as n approaches infinity, an is equal to 0. And that's what we wanted to show. So now, it is important to note that this theorem over here is not true in the other direction, meaning that if the limit of the sequence is equal to 0, then the series converges. That is not actually true. For example, let us take the sequence of 1 divided by n. We know that, well, since the limit of 1 divided by n is equal to 0, however, this series, the harmonic series, we know that diverges from the example we had a look at earlier. So it's important to note that this series is only true in one direction. So meaning that if only the series converges, then the limit of the sequence is equal to 0, not the other way around. However, another theorem that we could have a look at is an alternative version, but we sort of had a look at the contrapositive of it. So the theorem now says, if the limit of an does not equal to 0 or does not exist, then the series diverges. For example, let us show that the series given by this diverges. So we compute the limit as n approaches infinity of this part here. So we show that the limit as n approaches infinity, n squared divided by 5n squared plus 4. We know that is equal to 1/5 here, just by inspection here. And that does not equal to 0. So by theorem 7.2.2, the series diverges. All right. So that is actually going to be all for this section over here. So the next lesson, we will move on to have a look at the convergence test for a series of real numbers. So the first part we'll have a look is the integral test. The next part after the integral test is going to be the comparison test. And the alternating series, absolute convergence, ratio and root test, and all that we will have a look at the next lesson and maybe the lesson after. So this will come in about 2 or 3 videos to come. So anyways, if you guys have any questions, just feel free to leave them in the comments down below. And so I will see you guys in the next video.